Single bond, double bond, triple bond, quadruple bond, quintuple bond, sextuple bond. Where I should stop? Which is the highest possible? So we have many 6. We have 4. We have 2. We have 8. Everything? Somebody said something else too? Probably this. I start from this. This is a difficult question. If you do experiment, you see one atom, you see second atom, but between them you see nothing. You don't know if there is 1 bond, 2 bonds, 3 bonds. The single, double, triple, quadruple bond is only inside our head. Okay? You can think in the terms of orbitals, but you don't see orbitals in experiment. So people are arguing a lot. What is the highest possible type of a bond? And as an example, I brought 2 papers. This one is from this year, and this one is from 2005, 2 years ago. Okay, this one is published in Nature. This is the best science journal in the world. Okay? And this one, it says, quantum chemical calculations show that the uranium molecule U2 has a quintuple bond. Okay? So why I'm showing this to you? Because the information is people still don't know what are the bonds in most of the molecules, especially complicated molecules. U2 it's a uranium. If you look somewhere there and you look for the uranium, you will find that uranium has the atomic number equal 92. And it's at the bottom of the periodic table. So to answer how many strokes you should write for U2, a simple molecule, only 2 atoms, the answer could be given only 2 years ago. Okay? And this one, the title of this paper is Reaching the Maximum Multiplicity of Covalent Chemical Bonds. So what I wanted to show you by this paper from this year, published, well, it doesn't say which month, but I think it is something around June. So a few months ago, it's that people still don't know what is the highest maximal bond and if it can be reached or not. Okay. And this paper says, over the years, we have studied several metal-metal multiple bond compounds, including complicated ones. The highest bond order one might expect is 6, involving 5 DD and 1 SS bonds. But at the same time, the other paper that I was showing you gives the orbitals, bonding orbitals, and some of the bonding orbitals are the F orbitals. It looks like the F orbitals can also make a bond, but that would be very, very, very weak bond. So the most important thing that I want to tell you is that the number of strokes you put between 2 atoms exists only inside your head. I always put 1 because I don't know how many there is in reality. Good. But your book is giving you a recipe for putting a correct number of strokes and getting single, double, or triple bond, and you should follow these patterns. Good. This is one thing I wanted to clarify. We are closing the chapter 2 and chapter 3, so I will be looking through the book now and telling what else we should study, what we studied. If you have some questions, now is generally a good time to ask them for the chapter 2 and the chapter 3. Probably for chapter 2 we discussed everything, I believe. More than everything, I would say. No, not everything. Yes. CH4, everybody knows how it looks like. But turns out that there also exists another form of C and H, namely CH2. I know it's rather surprising for many of you. This is called methylene. And if you write Lewis structure, the Lewis structure for these things would look something like that. This is strange. It doesn't follow any rule that we learned, but such things exist, and there are many of them. And we should study 2 another examples that are called radicals and biradicals. So radical is a molecule with unpaired electron. And biradical is a molecule with 2 unpaired electrons. Examples. Somebody gives me an example. Sure, both. Once again. Louder, I cannot hear you. CH3, nice. If you cut this bond, but this is a dangerous thing because you can cut this bond in 3 possible ways. 1, 2, 3. If you cut this bond in this way, you are getting the cation. If you cut this bond in this way, you are getting anion. If you cut it in the middle, you get radical. So be careful. CH3 radical, correct. Another one, simple ones would be, for example, lithium atom. It has an unpaired electron. Another one would be the OH radical. And there are many possibilities. Biradicals. Well, we already know that O2 is a biradical. It has 2 pi orbitals with single electron on each of them. Okay. And your book is giving some other examples of biradicals. For example, like this. C, 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 H, H. Now, why they are important? Because they are extremely reactive. Another way of getting or writing many, many different radicals is take atom A with even number of electrons and atom B with odd number of electrons. For example, you can make NO, NC, SN, SB, and you can go for the list for a long, long, long time. All of them have unpaired electrons. So these are very reactive molecules, and in fact, these are radicals that decide in large degree how long we are living. If somebody has good mechanism to kill, to cut radicals in the body is not destroyed fast. But when somebody is getting old very fast, it means that the mechanism to destroy radicals doesn't work very well. And the chemical reactions in our body are happening too fast. Good. This is another thing. Now, another thing from your book. Your book first is introducing the Lewis structures, and then for the next 50 pages is telling how bad the Lewis structures are. So we went a bit around. We went to the orbitals first, and we introduced the Lewis structure later. So we are not going to say about the exceptions to the octet rule, because, I mean, by default, we don't really care about octet rules too much. So there is something like expanded valence shells, which more or less means that there are elements with more than 8 electrons in the Lewis structure. And the best example of such atoms are sulfur, iodine, bromine, what else? I guess chlorine would be fine too. Probably phosphor would be fine. Generally, all the transition metals would be fine. What does it mean? Let's think for a moment. If you have a metal, atom A, and this atom has 8 maximally 8 electrons in the Lewis structure, it means that the atom can have 4 bonds, not more. If you need 5 bonds, there would be already 10 electrons here. 6 bonds, there would be 12 electrons. So to get more than 4 bonds, you have to need more than 8 electrons in the Lewis structure. If you have this situation, we are speaking about expanded valence shell. Not much philosophy. Another thing is that some of the bonds can be not a real bond, it can be a lone pair. It also counts. And the examples of these molecules is, for example, PCl5. It's I3 minus. That the Lewis structure for this one looks probably something like that. I, 1, 2, 3, 1, 2, 3, 1, 2, 3. Of course, minus. And as you see, 1, 2, 3, 6, 8, 10. 10 electrons for this iodine, 8 for this, and 8 for this. And I suggest that you read something more about these expanded valence shells. Probably it will be one of the questions at the midterm. So you can prepare to this. Oh, there's a nice example. I think we should study this for a moment. If you think about NH3, the NH3 looks like that. There is a nitrogen atom which has a lone pair and it has 3 hydrogens. Now there is another molecule which is BF3, and BF3 is a strange molecule because first it's flat, which is not very strange, but another part is that if you look at the valence structure, it has only 6 valence electrons and is happy already. So the Lewis structure again doesn't work for this molecule, but in the other direction. It doesn't go to 8, it goes only to 6. But now these 2 molecules can react together, and the reason for that is that this molecule has empty orbital p, and this one has a lone pair. So together they can make a donor-acceptor bond, and finally it looks like that. You have N with one of the hydrogens, and the lone pair makes a bond, and after making the bond, this structure is not flat anymore, it's also becoming 3-dimensional, like that. I kind of like this molecule. So we have a donor-acceptor bond. Good. And that's, I think, good moment to finish chapter 2. What time is it? 10:15. well, 10:07. We are making 20 minutes break. And we are meeting 10:27. And 10:27 we are going to have a class for 40 to 50 minutes. And then you are going to write a quiz. Thank you. Okay, we finished chapter 2. And we almost finished chapter 3. Tomorrow we are going to discuss so-called VSEPR theory. I may call it sometimes shortly VSEPR. Don't follow me. This is VCEPR. So that's for tomorrow. And today let's discuss something else. Good. We said that the molecule can have the following shapes. We were discussing hybridization some time ago. So we know that the hybridization SP gives you this molecule, sp2 gives you this shape, sp3 gives you this shape, then dsp3 gives you this shape, and D2 sp3 gives you this shape. But this is only the shape of the bonds or the lone pairs. This is not necessarily the shape of the molecule itself. What I mean by it's not the shape of the molecule, these bonds can be occupied, these positions, these 6, 5, 4, 2, 3 or 2 positions can be occupied either by bonds or by lone pairs. The lone pairs you don't see, bonds you see because there is another nuclei there. So now we have to analyze what possible shapes we can have. Now in this case, the molecule will always look like that. When the dots means atoms. In this case, we have 2 possibilities. One possibility is that at the end of every stroke there is an atom. And second possibility is that at the end of the stroke there is no atom. It means we have a lone pair. Then maybe it's good to remove this. Now, similar situation can happen here. First is at at the end of every stroke there is an atom. Or there is one lone pair. You know, I write the lone pair up. They will be looking probably more familiar to you. Atom, atom, and there is a lone pair. Another possibility is there are two lone pairs. And another possibility is there are three lone pairs. Similar thing can happen here. But here the interesting story can happen already at the starting point. We can give the lone pair here, or we can give the lone pair here, having two different types of molecule with four atoms. So once the lone pair comes here, making very strange shape of a molecule, and another case, the lone pair is replacing this atom, having this shape. Of course, we should write also the full structure. With 5 atoms. When we have two lone pairs, there are two possibilities. One of them comes here and another one goes there. Or, and you can imagine all the other possibilities. There's quite many of them. And finally, the important part is the next one, when we have three lone pairs. And similar story can happen here. Full structure or structure with a one lone pair. And again, a lot of writing here, but I just finished the structure with 4 lone pairs. So there is quite a lot of work to write all of these structures, but if you go to your book on the page 96, there is one big table with all of them. Page 96. And all of them have a name. So let's write the names of them. You denote the central atom by A. You denote the terminal atoms by X. And so on and so on. So this one is called AX3. This one is called AX2. This one is called AX2 and one electron lone pair. And there is not much philosophy about this. This one is called AX4, AX3E, AX2E2, AXE3. Okay. My point is that you should be able to write all of them, which is not much philosophy, just systematically write all of them. And you should be able to show at least one molecule for each of the types. So what are the molecules? For example, in this case, you can say beryllium chlorine 2. For this molecule, we just studied in the previous hour, it was BF3. For this one, for example, what? O3 probably would be working here. SO2. Here, for example, CH4. Here, for example, NH3. In this case, for example, H2O. This example, for example, I don't know, HCl. So it is kind of interesting because when you think about HCl, the corresponding Lewis structure looks like that. HCl. And you may think that these three bonds are at the angle of 90 degrees. When you look at this picture, you see this is not 90 degrees. The angle between them is 109 approximately. Now, few remarks to the shapes obtained here. This molecule, given for example by, in your table you have ClF3. So you see, for some of them you have to go to very special cases. It's called T-shape. And the reason is understandable. It looks like letter T. And another interesting molecule out of these is this one. Seesaw. You know what it means in English? Yeah? How do you say in Chinese? And the reason is, if you look at this, these are the standing parts, and this is the bar. So the bar can go like that. So this is the shape of the seesaw. And the example for this one would be SF4, for example. Good. We discussed sigma bonds, pi bonds, hybridization types. Usually discussed almost everything. Bonding, non-bonding. Aha, yes. Now we are going to discuss the shape of the orbitals for more than 2 atoms molecules. We said when we have 2 atoms only, the bonds can be divided into sigma, sigma anti-bonding, pi, pi anti-bonding, delta, delta anti-bonding. We defined this before. Now we go to the next situation. We have 3 atoms, linear structure. Except for the sigma and sigma antibonding, pi and the pi antibonding, and delta antibonding, we are going to have also the next possibility, so-called non-bonding orbital. Pi non-bonding and delta non-bonding. To understand what is non-bonding orbital would be very easy. Take, for example, H3 molecule. I know that H3 molecules for you sounds a bit strange, but we can assume for a moment that H3 molecules exist. And we know that the S molecule would be made by overlapping one S of first hydrogen, one S of the second hydrogen, and one S of the third hydrogen. Now, we said that if we have one S plus linear combination with one S and plus linear combination with one S, we are going to get an orbital that looks more or less like that. And clearly that would be a sigma orbital, because if you look from this direction, it's round and it has no nodal surfaces. Now when you combine one S with the plus sign, here was of course also plus sign, minus 1s plus 1s, then you are getting something what looks more or less like that. I first start by writing what I wrote on the previous blackboard. And now I know that the change of sign here makes a nodal surface. So the nodal surface looks like, it's not easy. And we see that the sign here was plus, 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 and the sign in this orbital is plus. But here the sign would be plus, minus, plus. And this was sigma orbital. This is the sigma antibonding orbital. So the question is there something between them? There should be, because this orbital has 0 nodal planes. This orbital has 2 nodal planes. Between 0 and 1, there is 1 nodal plane. How the orbital can look like? First, it must be symmetric. If this is symmetric, it means that the nodal plane must come exactly in the middle. If the nodal plane comes exactly in the middle, it means must be 0 here on this atom. So it means that the coefficient for this one is 0. 1s, and it doesn't matter if it's plus or minus. And then we know that the must change sign, so it will be plus minus. So the orbital in the middle will look something like that. And this is called non-bonding orbital. The reason for bonding and non-bonding here is a bit strange. Before we said that if the orbital has no nodal planes, it's bonding. If the orbital has nodal planes, and this one has 2, it's anti-bonding. Well, according to this definition, this one has a nodal plane. We should call it anti-bonding. But the reason is, if you plot energy, 1, 2, 3, these are the energy of this one, energy of this, and energy of this one, and that's the 1s. And if you make 3 bonds, the sigma will go down. The sigma anti-bonding will go up in energy, but the sigma non-bonding will have similar energy. That's why people defined a word non-bonding. Well, similar story happens for pi orbitals. If you have first hydrogen, second hydrogen, and third hydrogen, and you have the p orbital, you have the p orbital, and you have the p orbital, they can again make a linear combination with plus minus sign or with 0, as we said. And we see that px of the first atom plus px of the second atom of the px of the third atom gives something what looks like that. this region merge together. These regions merge together. With the plus sign and with the minus sign. Then the antibonding one would be px on the first one with plus, minus px on the second one, plus px on the third one. And this one will look more or less like that. I mean, generally that's already the end of the story. Plus, minus, minus, plus, plus, minus. But there is also the third linear combinations out of them, which is the px on the first one with plus, plus 0 times px on the second minus px on the third one. And this one looks like that. Nothing here. And the sign is plus, minus, minus, plus. So you see that this one doesn't have any nodal planes. There is no sign change, bonding. This one has two planes, 1, 2, when the sign is changed. And this one has only one plane when the sign is changed. This is the pi orbital, this is the pi antibonding orbital, and this is the pi non-bonding orbital. And for delta it goes the same. And again the same story for the pi's like here. If I put just pi, pi, and pi, and here is px, that would be true. Good. 2 and 3 atoms, more atoms. Planar. What does it mean planar? Planar means that all the atoms are in one plane. Two-dimensional structures, kind of. So we can say here it's 2D. And what is the examples of a planar structure? H2O would be, because all the atoms are in the same plane. Well, from the mathematics you know that 3 points make a plane, so they cannot be. Oh, we have a dog listening to us today in the class. Interesting. Another one would be BF3. That looks like that. But another one would be, for example, C6H6. All of them are planar. So for this planar, we still have sigma and sigma antibonding and sigma non-bonding orbitals, and still have pi orbitals and pi antibonding and pi non-bonding orbitals. But now the definition is different of pi and sigma. Because here to define the sigma, pi, and delta, we are looking through the axis crossing the atoms. Here there is no such axis. Which axis? There is no one axis connecting atoms. But there is a plane. So we can look at the plane connecting atoms, and let's imagine that's the plane. We can have two possibilities. First one, the orbital is symmetric with respect to the plane. This is the sigma orbital. But if the orbital looks like that, that on one side of the plane is plus, but on the other side of the plane is minus. This is pi orbital. Good. Let us write some linear combination similar to this one for larger molecule. Let's start with the pi orbitals. Somehow pi orbitals are easier. Let's imagine the molecule that looks like that. C, double bond, single bond, double bond, H2, H2, H, H. Okay. Now, when you look at this molecule, you see that each of these carbon atoms, all of them are in one plane. Like carbon, 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 hydrogen, 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 hydrogen. I guess you cannot see anything. I use maybe colors. Carbon, 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 hydrogen, 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 and hydrogen. Now, each of these carbons has a pi z orbital. With the plus sign, the minus sign. Now these 4 pi orbitals can make the linear combinations with the plus sign or the minus sign. Now let's try to design a linear combination with 0 nodal planes, 1 nodal planes, 2 nodal planes, and 3 nodal planes. With 1 nodal plane it's easy. It will be just plus, 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 plus. all of them, and the orbital will look something like this. Plus, minus. It's also easy to do it with the 3 nodal planes, because then it would be plus, minus, minus, and the sign is plus, minus, minus. And here the linear combination is plus, minus. What about 1 nodal plane? Also easy. Plus, minus, minus gives you something what looks like that. Plus, minus, plus. And with 2, also easy. Plus, minus, plus. Gives you something what looks like that. Plus, minus, plus, minus. No nodal plane, 1 nodal plane, 2 nodal planes, 3 nodal planes. If you plot energy of 4 of them, 1, 2, 3, 4 at the beginning, all of them have the same energy, you get just splitting like that. Now, which one we called bonding here? Which one is anti-bonding? Well, clearly this is a bonding. Clearly this is anti-bonding, but these one have nodal planes too. We should call them anti-bonding. But what we really use to decide if they are bonding or anti-bonding is the energy. If the energy goes down, it's bonding. If the energy goes up, it's anti-bonding. So now, 1, the lowest energy is this one. Bonding. Second, bonding is this one. Next one is this one. And this is anti-bonding because the energy went up. And 4 is anti-bonding because the energy went up. So it's not very difficult to make these orbitals. Just some imagination and counting how many nodal planes. Now we do something more difficult. We go to the benzene molecule and we try to find what orbitals are making this pi bond, this circular pi bond. So we start with 6 pi bonds located on these carbon atoms. Now you can combine them with the plus or minus. And let's try to combine them that way that they have 0 nodal planes, 1 nodal plane, 2 nodal planes, 3 nodal planes, 4 nodal planes, 5 nodal planes, and so on. Oh, in this case it's easy, just 6 times plus. If you put plus everywhere, then you see that the upper part make a circle like that with the plus sign, and the lower part of the orbitals make another circle like that. With the minus sign. With 1 nodal plane, generally there are 2 possibilities. The nodal plane can go between orbitals, dividing them 3 and 3, or the nodal plane can go on orbitals, dividing them 2, 2, 0, 0. And it's true. The possibilities are plus, 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 minus, minus, minus. And I write this possibility in the following way. It will be not easy. let's do it slowly. 1, 2, 3. But now they are changing sign in the half. Plus, minus, and that one that is below not very good picture, but I cannot probably do better. Plus, minus. And another one will look virtually the same, but another one will have what? Will have 0 plus, plus, 0 minus, minus. And the other one will look like that. Minus, minus, plus, plus. Okay. Then you have the next ones, and you see that the next one must change sign twice. That one changing sign twice may be, for example, plus, plus, minus, minus, plus, plus. No, not good one. And the reason why this one is not good one is that maybe it's changing sign twice, but it's not symmetric. There are 4 pluses in a row. There cannot be 4 pluses in a row and only 2 minuses. The number of pluses and minuses must be the same in the structure, or like that, 0 of them. So this is not good one. And if you think about that longer, you can put 2 planes like that. This is one way of doing this. So there will be plus, plus, minus, plus, plus, minus. But now, to avoid the minuses being only twice, you put a coefficient 2 in front of them. So they will be a bit larger here and here. But we just skip the coefficients. And another possibility is that this is one of them, and the other one, once it comes between these, and the second time it comes on those. So the other possibility is plus 0 minus, plus 0 minus. And finally, for the third one, would be the plus, minus, plus, minus, plus, minus linear combination. Now, if you make, I'm not going to plot them, but if you want them to see them, they are printed in the page 115. All of them. And again, you can start with the energy. We have the energy axis. Here is the energy of the 6 orbitals of carbons, 6 of them, the same. And now one of them is bonding pi. Two of them have the same energy, they are degenerated, also bonding. Two of them are unbonding and they are degenerated. One of them is unbonding and not degenerated. Which are which? The lowest one is this one. This one, 2 and 3 are these two. 4 and 5 are those with 2 nodal planes, and 6 is that one with 3 nodal planes. 6. So as you see, molecular orbitals for many atom molecules sometimes can have complicated shapes. And nothing can be done about this. Okay, we finished the class today.